This PowerPoint is about current and resistance, and we should really talk about voltage as well, but we'll do that in a future PowerPoint. So we've talked about static charge, so it's charge that stays still and builds up inside you, like the Van de Graaff generator, or like a cloud, a thundercloud, building up a charge, and it gets stronger and stronger and stronger. But now we're going to start talking about sort of conventional electricity, which is the flow of these charges through a conductor. Now there's a key term here, current. You might want to write down in your notes that current is how fast the charges move around the circuit. And a nice diagram of this here on this slide shows these little blue moving charges or electrons flying through the wire. Now what happens is every so often one of those electrons is going to bump into an atom, bump into one of the positive nuclei of an atom and transfer its energy to it, and that's going to come out in the form of heat. So all these collisions between electrons moving through the wire and the nuclei, which I showed you in the previous video on static, that generates heat, and that's called resistance. So there's a second key term, resistance, a material's opposition to the flow of electric current. So if I turn the resistance up, the current slows down. And if I turn the resistance down, that allows more current to flow. And it's all to do with collisions. It's all to do with electrons banging into atoms as they move through the wire. In this case, it's probably copper atoms, because usually electrical wires are copper. Where else do we see the word current? We're going to get into some analogies now. Analogies are quite good for, I find, teaching and learning about electricity. Rivers. We use the term with rivers, don't we? We're not talking about the currents you find in current buns or anything like that, but in rivers, current means how fast is the water flowing. So it's quite a nice analogy. In electricity, it's how fast the electrons flow. So I guess you could say the river itself, in my analogy, is the wire, and the water is the electrons, and how fast they flow is the current. Another good analogy for electrical current is the idea of a rope moving through your hand. You're not grasping it, but it's touching your hand, and the rope can be moved through your hand. Now what's going to happen if this rope moves through your hand? Well, it's going to deliver energy to your hand because of the friction, and it's going to get very hot, and you're going to get rope burn. Now that's a good analogy, because the electrons flowing through the wire, banging into all those atoms, that creates friction too, and that generates heat, and that heat causes the filament in a light bulb to glow. So it's the same kind of idea. A rope being pulled through your hand generates heat and burns you, and a current of electrons, of charges flowing through a wire, causes resistance and causes it to heat up and therefore give off light. So let's explore this analogy a little more. If I ask you the question, why does your hand hurt more when I pull a rope quickly through your hand? It doesn't hurt if I pull it slowly through your hand, because it doesn't generate enough friction and not enough energy is transferred. Well, let's take it step by step. When the rope is pulled quickly, there's more friction between the rope and your hand. More energy is transferred to your hand in the form of heat, and because it's hotter, it hurts more. Now let's go from the analogy back into the sort of the electrical explanation. Answer this question: why is a light bulb brighter when the current is higher? It's quite a similar question. When the current is high, those electrons are moving very fast. The friction of the electrons rubbing against the atoms and banging into the atoms in the wire causes a build-up of heat. The wire in the bulb gets so hot it glows, and the hotter it gets, the brighter it glows. So it's kind of a similar thing. It's about how fast are the electrons moving through, and therefore how much energy is being delivered to the bulb per second. Now, it doesn't have to be a bulb, it could be anything. It could be a motor, it could be a buzzer, or any sort of energy change. But what I'm trying to get to you, what I'm trying to explain, is that the faster the electrons move through a component, the more energy is delivered to it per second. Going back to the resistance, back to this diagram of these electrons moving through the wire and occasionally colliding with these atoms, a good analogy that I like to use for this is the crowded corridor analogy. Imagine you're running down a corridor and there's lots of people in your way. You're an electron and you're banging into all these people as you try and tear down this corridor. the people in the corridor represent the atoms that you're banging into, and every time you collide with one of these people in this corridor, you deliver a little bit of energy to them in the form of heat. If there were no one in that corridor, you could run down that corridor really, really quickly. So this links back to the idea of resistance. The thinner the wire, the higher the resistance, and you can appreciate why using my analogy. A thin wire, or trying to run down a thin corridor, a narrow corridor with crowded people, is going to be very, very difficult. If the corridor is wider, then it's obvious that it's going to be easier to run down the corridor, and that's the same with electricity. With electricity, if you use a thicker wire, there's more room for the electrons to run down, and so the resistance is reduced. And if the resistance is reduced, the current is higher. And also, the longer the wire, the higher the resistance. Your whole journey down that wire is going to be more difficult because there's more overall resistance. There's going to be more collisions. So that's kind of an analogy for resistance, the crowded corridor analogy. Looking at actual resistors, if you've ever taken anything apart, anything electrical apart, and you've seen some of the sort of gadgetry that's in the circuit boards, and those green circuit boards, you quite often see a lot of resistors, and they look like this. You can also get something called a variable resistor, and the symbol for that is a rectangle with an arrow pointing through it. A variable resistor, you can move the resistance up and you can move the resistance down again. So if I move the resistance up, that's kind of, in my crowded corridor analogy, that's kind of like more people running into the corridor. It's harder for the electrons to move through the conductor. And if I move the slider down and there's less resistance and there's less people in that corridor, and the current can flow much, much faster. So that's a basic introduction to what current and resistance are. And I don't know, I find those analogies quite useful. Lastly, this is Ohm's triangle. Now the V stands for voltage, the R stands for resistance, that's obvious, but the I stands for current. And the reason for that is because C is being used for something else. So I is current, so don't get confused by that in the future. So if you want the equation, if I asked you to find current, for example, you'd cover the I, and what you see is the V over the R. So I equals V over R, V divided by R. Resistance is V over I, so cover the R up, and what you see is the V over the I, V divided by I. And if you want to work out voltage, it's I times R. So you've got three equations in that. All you need to remember is VIR. So let's move on to some questions now. If you pause the video here, have a go at these questions, and then the next slide will tell you if you got them right or not. Good luck.